Thanks for joining the ESIP Wildfire Cluster's November meeting. Today we have Kyle Dietz-Mann and Howard Butler from Hobu, who are developers of the SilviMetric tool. This is an interesting cloud-native approach to forestry metrics from lidar datasets, and has been an interesting thing in the lidar space for several years, and I'm excited to hear the current updates. All right, Howard, Kyle, go ahead.
Thanks, Tim. Kyle, you want to share out our slides?
Yeah. Let's see here. Can you guys see that?
Not yet.
Okay. Sorry. Oh, whoops. Okay, there we go.
Yep.
Okay,
Good.
excellent.
Awesome. So thanks for the intro, Tim. Again, my name's Howard Butler, and we have Kyle Dietz-Mann from Hobu as well. We're both open source developers. Our background comes from doing a lot of lidar data management, and so you may have seen us active in projects like PDAL or PDAL, Point Data Abstraction Library, and of course some of the other open source tools that are commonly available, like GDAL, Proj, things like that. Next slide, Kyle. How we get to this particular topic, SilviMetric, is just how to turn all this massive lidar point cloud data into something that you can do, actionable data in the forestry space, which tends to be not point cloud data oriented. And there's just hundreds and hundreds of terabytes of this content available now, and managing that is quite a data chore if you've tried to do this yourselves. And our perspective on it is to try to do things to make the management of the point cloud data easier. So that's things like the cloud optimized point cloud and entwined point tile, if you've seen those, and working with organizations like USGS to provide all of the 3DEP data available on an open public data set, and also to make it more convenient for people to process those large data with open source tools. Next slide, Kyle. So what are the needs as we see them for something like SilviMetric is, users want to be able to produce standard products in some sort of data-driven cloud infrastructure. So, take advantage of the ability to dynamically scale computing to try to overcome this large data problem. And then once that process is done, make it conveniently consumable by, data analysis tools, data science tools, typically like Jupyter Notebook or something like this, and eventually be able to do this in some sort of automated way as data comes into the system, pop it through the crank and have it come out the other end and be available for access and use. Next one again, Kyle. So, our ultimate goal is to be able to provide something that could represent an entire continent worth of lidar forestry metric data, and have that data sit out in the cloud somewhere, be compatible with existing tools that everyone has access to, and allow users to be able to, extract the information that they need in some GDAL readable way, be able to provide their own customizable metrics that they might want to compute as the data is processed, and then have this entire thing be open source. Kick down, Kyle. So why don't you pile in here, Kyle?
Yeah, so we kind of see SilviMetric. I mean, there's already a lot of tools available within kind of the forestry area, and we see SilviMetric trying to fill in a gap that's there, and that gap is mostly around data management, as we've already talked about. The ability to take take data and to store it in the cloud in an easily accessible way. So that means like spatially organized data that's easy to access, that's easy to query, and that is available for people to touch and to collaborate with. I think that's kind of the big area of need that we're seeing. There are other key areas that we're seeing, like lack of format abilities. So there are quite a few libraries that can only interact with LAZ or LAS data. Through the use of Poodle, SilviMetric is able to interact with a lot more different types of point cloud data. The SilviMetric can ingest a Poodle pipeline. So any kind of processes that you want to have before you're actually operating can be done, and so it's a flexible product. A lot of the other products don't speak cloud, so it can't integrate directly with S3 or Google Cloud or Azure, and don't have direct access to EC2 instances, to Kubernetes clusters, and just general cloud capabilities. SilviMetric makes use of Dask primarily for interacting with, or Dask and TileDB for interacting with cloud infrastructure. Mostly Dask for its parallelizable structures, and TileDB for interacting with the actual data that's stored there. Some of the previous iterations of this kind of software, like Fusion, require the ability to read and write C++ code, which is not necessarily a low barrier of entry. Like that requires quite a bit of time to understand and figure out how to actually interact with it. And within the forestry metric kind of area, there's kind of a lack of mature Python code. There are some libraries that have been created, but not a lot that have been picked up and have a lot of steam. And there are some that are even just direct ports from R. So yeah, so we see SilviMetric as being easier to use than some of the previous iterations of this. So we had originally been working with Bob McGaughey from the U.S. Forest Service and USDA to develop sort of a modernized version of Fusion. And our kind of modern approach to this was using cloud infrastructure, using Python to make it more easily accessible for developers, and using TileDB to make it compressible and to make it far easier to access the data and make it spatially organized. So yeah, so we incorporate Python for much easier or more like well-used workflows for like data science, specifically with NumPy and SciPy and Pandas. And then we use TileDB and Dask for our cloud infrastructure. Poodle allows us to really interact with data in a very flexible way. Since Poodle has like over 30 different formats that it covers for reading and writing, you can really interact with most different types of data. SilviMetric does require that the data be spatially organized. So in order to, so we would need to translate anything. So if we have a Poodle pipeline that's coming in, it would have to, like if we were reading an LAS file, it would need to be converted to like COPC or EPT within the pipeline, and then that data can be managed by SilviMetric. Poodle allows us to crop, reproject, filter, and transform data. It also allows us to do things like run HAG and create to classify points as ground and to normalize point clouds. Poodle is open source, which is very useful and allows us to remain open source as well. And it is easily installable via Conda and Docker. And with the Poodle Python bindings, it's easy to install with pip as well. TileDB is a multi-dimensional array storage format. It's very similar to ZAR if we're thinking in terms of dense arrays. But what makes TileDB very interesting and what they kind of did first is that they uh, made it easy to interact with cloud resources and made it easy to compress data as well. So TileDB has a built-in virtual file system that allows you to interact with S3, Google Cloud, Azure, and I think DigitalOcean as well. And so your data can be easily stored directly, stored and accessed directly from your command line or from a Python script, and then manipulated from there. TileDB is high performance. There's a lot of filters available, including like gzip filters, Z standard filters, and then quite a few others that allow for compression and speed optimization. The TileDB also has infinite sized arrays, so we can theoretically create as big of an array as we want, which is kind of useful for these kinds of tasks where we may not know immediately how big we want to make our array.
So TileDB comes from the genetics space. And so that's where it kind of has grown up and cut its teeth, where, they're doing really large, very high dimensional arrays. And so they want to be able to segment and put those in the cloud. And so, TileDB, the company, was working in the geospatial domain for a while, building up some capability there. And so we're taking advantage of some of that capability with SilviMetric.
TileDB is also once again open source, or at least there is an open source section of it. They do have a paid version as well, but for our purposes, all we need is the open source section. It's also conveniently installable via Conda and pip, and supports quite a few languages, including Python, R, C++, Java, and Go. So now we'll kind of dive into the process behind SilviMetric, how we kind of envision data being handled and being conceptualized. SilviMetric works mostly with two main pieces: the attributes, which are represented by like poodle dimensions. So like think like X, Y, Z, height above ground, intensity, stuff like that. And this point data will be stored in TileDB as a variable length array, and allows us to reference this point data later after the TileDB array has been created. Our main form of derived data is a metric. A metric represents data that is going to be that has been derived from the point data. So think like 95th percentile of Z. We have our initialize, which is a creation of database stuff. Info, which gives us information on our database. Scan, which gives us information on a point cloud that we might be ingesting. And I'll be doing a more in-depth analysis on each one of these as we're going. But I'm just kind of giving an overview. Our shatter is our main process, our main workhorse. So this is splitting up data, running our algorithms over it, and then writing it to TileDB. Extract pulls out raster data from that, and manage allows us to manage the data that's already been written to TileDB. So yeah, like I said, attributes represent poodle point dimensions, X, Y, Z, intensity, stuff like that. And we represent them with NumPy data types and pandas array extensions. And while all poodle dimensions are accepted and valid, you can also make your own dimension if you'd like. So if you wanted, if Z hadn't been created yet, then you could easily make a new attribute called Z with like a NumPy float 32. Let's see. Metrics are our main derived data. We I've already implemented a lot of metrics. Like I said earlier, this is meant to be, or SilviMetric in its creation was meant to be sort of a modernized version of Fusion. And Fusion has a suite called the grid metrics, which has, I think, around 100 different metrics that are produced. Fusion does write out each one of these directly, so it ingests one point cloud file and outputs a directory of like 100 different raster pieces. And so we are taking this data, we are running all of these algorithms over them, deriving all this data, and then we are storing it later for somebody to use. So it's not just sitting in a directory somewhere. Here's a more in-depth analysis on metrics themselves, because they are quite complex when we dive down into them. We don't want to be since we don't have the benefit of running C++ code like Bob does, we kind of have to make sure that we're running things efficiently and we're not rerunning any kinds of methods that we don't have to. So metrics can have filters, which allows the data to be filtered before it's being processed, and dependencies, which allows one metric to depend on another metric. So if you have 5 metrics that all need the mean of your z values, you don't want to run mean 5 different times. Like, it's much easier to run mean once and then pass mean to each one of the follow-up metrics that come after that. Same thing for things like percentiles. There's no need, if you need 100 different like if you need all the percentiles, there's no need to run it 100 different times. You might as well run it once and then pass it to each follow-up metric after that. So as you can see on the right here, we have some definitions from like the grid metrics suite that are good examples of this. Our all cover metric, which is all of the returns above a height break. So that's by default 3 meters, divided by the total returns above the min break, which I believe is 2 meters. So we have a dependency of the counts metric of the all count, which is defined in our dependencies here. And then we select only the return number attribute. So we're not doing this all over Z and intensity as well. We're only doing it over the return numbers. And we are using the all counts as a dependency. We can also look at some of the count metrics to see filters as well. If you look at the first count above height break, which is the bottom one in the dependencies, you can see that there's a first returns filter. And so by applying this filter, we are removing everything that's everything that's not the first returns, and then we can get the count from there. So all the metrics end up being like pretty simple, like easy to run, easily parallelizable metrics, but they all need to be run as quickly as possible over something like a pandas array. Pandas data frame. The first step in our workflow is the initialize step. This is where we're creating our TileDB array. We need to know information about our data beforehand, things like our bounding box of the data. We'd like to know this ahead of time. We need to know our coordinate system. We need to know what metrics we want to run over it, what attributes are being applied to it, and the work unit size. And this allows us to be more efficient with how we're splitting up data, so that we can work within the confines of TileDB tiles. TileDB also has a very interesting concept called time travel, which allows us to, so when we write something to TileDB, we are writing what's called a fragment. This is just a piece of information that's been written, and they apply a timestamp to this fragment. So when we get to the end of all of our writes to this TileDB array, we should have X number of fragments. And if we have 5 different processes, 5 different shatter processes that have been run over data, we can look at each individual process and all of the fragments that are associated with that process. Because we store the timestamp of a shatter process into the config, we can easily look at all of the fragments in TileDB that are associated with a specific process. This allows us to better manage the data that's actually in there. So it's not just we're throwing this in there, and once it's in there, that's all you have. Like, you have to work with what's there. We can delete data that's already been put in there. We can rerun data that's already been put in there, and we can kind of coagulate it as well into a specific, or into one piece of information at the end. And so, as you can see from the little example on the side here, if we have 4 different runs, I mean, this is Autzen, but if we have like 4 different runs of Autzen, and we can essentially look at each individual piece by itself and manage that as its own work unit. So we can if we don't like what's done in the timestamp 1, we can remove timestamp 1 and rewrite all of that information with a different process. Scan is something that gives us a lot of information about the point cloud in relation to our database before we even run a shatter process. So this is something that we can run to figure out like point density and a prescribed number of tiles that should be grouped together to make a more efficient run of shatter. If we choose, so we can choose to do this before we run a shatter process, or it'll be run during the shatter process. If we run it before, it's kind of just like it's easier to run consecutive shatter processes, so that you don't have, like, if you have to retry it a couple times, then you don't have to run the scan every single time. So there's a benefit to running it beforehand, but there's also a benefit to running it during shatter. If we run it during the shatter process, then we can filter out empty extents, so we're not doing any no-ops as we're running through our process. The shatter step is the most complex part of SilviMetric, and is kind of the main workhorse. This is the part where we're going to be taking all of that data. We're going to be using PDAL to ingest it with whatever pipeline, or just reading the file. We'll be cropping it to any bounds. We will be splitting that up into more efficient tile sizes, and then we'll be running metrics over top of that. We'll then be writing that to TileDB at the very end. So all of this needs to happen in parallel at the same time, so we can make use of what we have in Python. And we want to be able to chunk this correctly so that it's efficient. We currently use pandas data frames as our unit of work. This makes it easy to manipulate data and to run algorithms over it in kind of chunk-wise fashion. Shatter also makes a pretty big use of Dask. This is kind of the most heavily used Dask area of SilviMetric. Here we are most interacting with our cloud resources, so it's easy to scale this stuff up, and it's very easy to kind of make it like as wide as you need it to be. So in this, throughout this presentation, we'll be talking about a specific data set called Boston Lot. It was created, it's a data set that's about like 1.7 billion points, and is highly variable, so it makes it really nice for testing like efficiency and testing whether or not things will run well. We are writing it at a 5-meter resolution, and as a testing data set, I've done 27 metrics. These are some of the kind of like core metrics that can be used to derive a lot of the other metrics available. With the kind of the main 5 attributes store, this is like your Z, intensity, return number, number of returns, and classification stored here. Our info call is something that we might call pretty much any time after we've created our database. But I find myself most using it to look at shatter processes that have already been run. So info will describe for us the database, will give us metadata on this, specifically our metric definitions, our attribute definitions, the bounds, and the CRS of our data. This also gives us a list of all the shadow processes that have been run and gives us all the information available there. As you can see, these are some of the examples here on the right. The bottom left one is our history example. And so it gives us the bounds of a specific run, as well as the UUID name or unique ID name, and the date range on this. So one of the other kind of key components of SilviMetric is that things should be able to be queried not only by bounds but also by date. So if we have a full set of a full state, there's probably a lot of different point clouds there. Some of them may even be overlapping, and so we want to be able to look at data that is actually, well, overlapping or rerun. Like there are times in which new data has been acquired, but it's not like you really want to get rid of the old data. And so if you want to look at Autzen from 2009 or Autzen from 2012, then you should be able to query that information by a date range, such that you only get the information that is within that bound, or that date. Extract is how we actually get our information out. So this is kind of the main point that we see like users actually interacting with us, SilviMetric data. So like the shatter is the part where somebody might be producing our data. Extract is the way in which somebody might actually be using our data. And so we've written our 27 metrics, and now somebody needs to use the 95th percentile. So somebody should be able to extract data by bounds, by date range, by metrics, or by attributes, and produce results from there.
I'll just add that
I'll go for
because it's TileDB, if you were like an R user or just a generic Python user, like that extract part is kind of what you're most interested in, right? So you don't have to go through this extract thing that SilviMetric is providing. We're providing convenience and logic to allow you to do that sort of stuff. But the idea is you would just connect to this directly with, maybe you have a notebook that you're just wired up to a TileDB, or maybe you have some script that's part of your process. And once the data has all been shattered into a TileDB, you do your data analysis or your or whatever you might have going on, and either connect directly through TileDB if you wanted to do that. You could also take advantage of SilviMetric if you were in Python land, of course.
Yeah, absolutely. Yeah. So Python is really only important in terms of actually manipulating SilviMetric. Like we said earlier, TileDB can be used from C++, Go, Java, and R. I know a lot of forestry work is done in R, so it was really important that we have some sort of tie-in there. So yeah, when we do an extraction of Boston lot, so this is an example on the right-hand side is the 95th percentile of Z, and as you can see the 2 lines of code that are at the very bottom there. It's super easy to extract data. You just tell SilviMetric what directory you're pulling from and what directory you want it put to, and all of the available ones or available metrics will be written out with that. Obviously, you can query by bounds, by attributes, metrics, and by date range to produce the data that you'd like from there. So yeah, so all you have to do is create an extract config, and then call SilviMetric extract from there. 2 lines of code. Manage is the way in which we most take advantage of the time travel feature in TileDB. So we have options to do things like resume. So if I don't know, if your instance accidentally shuts down or something, you get preempted, you're on a spot instance or something. We store the config for a shatter process in the metadata of TileDB. And then when we come back later, we can look at all of the or we can look at the non-empty domains that are associated with this this timestamp that from your shadow process. And that allows us to say, okay, what has already been run? Like if this, like we don't need to run you know, the entire data set again if we don't want to. So we can query for those non-empty domains and then compare them against what's already in there, or what's being sent to the shadow process, and then filter out any extents from there that don't need to be rerun. So resume allows you to to pick up a process where it was left off and just go again. Restart is kind of the same thing, except we're deleting all the data beforehand. So we look at all of the fragments that were written in that timestamp. We delete all of those fragments, and then we just run the shadow process again. So if you wanted to split up your data in a different way, then you might do that. If you messed up the dates associated with your data, maybe you would want to restart. You want to delete all that data, and then you want to apply a different date range for your shadow process. Then this makes it easy for you to interact with that and to essentially not have just bunk data living in TileDB. Same thing with your delete method. If you no longer want something there, you don't need that 2009 Autzen data anymore. You only want the 2012 data. Then you can just delete it, and there's no reason to keep it there if you don't want to. And so this makes our data a lot more flexible. It makes it easy for you to interact with your data in a way that that keeps it useful for a longer period of time. Here's just kind of a look at what I did to process Boston lot. So it's pretty straightforward for the most part. This is just a pretty normal Python script. In our storage creation, we're using something like PDAL to gather some information about our data. So we grab like the bounds, we grab the WKT, and then we just say this is where we'd like our storage config. These are the bounds. This is the WKT. This is our resolution. Our X size and Y size is kind of just our working unit. So if I want, this will kind of tell us like how much space should TileDB reserve for one specific tile. So in this case, it'll be like 10,000 cells are associated with one tile in TileDB, and this allows us in SilviMetric to be more efficient with our writes and reads there. Then we have like a pipeline for normalizing our data. The PDAL Python bindings make it pretty easy to create a pipeline directly from within Python. So here I'm just creating a reader of this COPC data and running the morphological filter over top of it, and then height above ground nearest neighbor filter over top of that. And then I write it out, and then I can reference that directly from SilviMetric as a file, and SilviMetric will use that pipeline from there. In the shadow process itself, I like to split up my data so that I can look at stuff as it's incrementally being added. So I do things like bisecting our bounds a couple different times and then creating a bunch of different shadow processes from that. So then I can incrementally look after each shadow process and make sure that things are looking good and that I'm efficiently writing things and that I can easily access my data. Oh, and then at the bottom, you can also see that I'm setting up a Dask cluster. So I was running this on my local laptop. So it's just so I was just creating a local cluster of processes. So that's just using like 12 cores on my laptop, creating a distributed client using Dask, and then when you run Shatter, it'll recognize that you have already created your Dask cluster associated with that, and it'll use those resources to create that. So if you wanted to create an EC2 cluster with Dask, then you could create that beforehand, and Shatter would automatically recognize that you are using that for your processing power. If you don't create a cluster at all, then Shatter will just use the basic Dask, which is splitting things into multiprocessing units, which uses Python's multiprocessor. This is more information about the Boston lot data. It was gathered in 2022 by Dave Finnegan, and is right outside of the Cold Regions Research and Engineering Lab, who we work with pretty extensively. Like we said earlier, has about 1.7 billion points, 11,000 acres, and a density of about 38 points per meter square. That is highly variable. So it's like that's an average, but it's much denser in some areas and much sparser in others. Here's a look at it from a Hobu ground. And I have not updated this. And you can follow us on GitHub. And we have a Jupyter notebook example on Google Colab available for use. And now I have time for any questions or comments, if anybody would like to.
That's awesome. Thank you so much. I'm curious about this from a sustainability of research software. There's a huge number of users that were really invested in Fusion, and particularly with the U.S. Forest Service. And that became impractical as the scale of our projects grew. And I'm curious about what your thoughts are on the approach to porting this to a much more sophisticated cloud native database schema as a strategy to make, to look back at and make, decision processes that are evolved in potentially a regulatory fashion kind of accessible into the future.
I mean, yes, that was very much the vision. And the grand wave of let's change the government all at once came by and kind of knocked us off the table. But I mean, that's kind of what our intent was. Like, what was the piece of software needed to essentially just sit in the background and grind data, and then make this available, make the metrics essentially available as a resource for researchers and administrators to be able to go to touch that data already compiled, already produced in a form that they can do stuff with without having to start from raw point clouds and build it all up from scratch themselves. And so, Fusion made it possible for the researcher to do that, but it didn't make it possible necessarily for kind of everyone else, because my joke is no one wants point clouds. They want what those point clouds have for information in them. And so, we maintain the public data set for the point cloud data with USGS, and still looking for resources to be able to kind of pull that off for a metrics data set that lives in one kind of single TileDB. Organized by time, as Kyle was talking about, that's like a key component of this, right? Like, we want to be able to segment by area and by time, but also, mishaps happen, data's bad, whatever the scenario, you need to be able to go back and jerk stuff out of it if it's no good. And so, that was also kind of an important design constraint here. And so that's where we have that whole part of it hasn't certainly been realized at this point. The parts we're good at is making awesome open source software and evolving things and moving forward with that. And so that's kind of where we're at right now. But hoping for someone in the future to go, hey, this fits our problem space really well, and we'd like to keep moving forward with it.
Yeah, and I'd like to, make sure anyone else have any questions. I could talk these guys for hours, but be sure, please.
Another key thing that the key assumption that SilviMetric starts with that Fusion doesn't is we assume that the point cloud data are organized in some spatially selectable format. And so for practical matter, that's either in Twine, point tile, or COPC. So you can either do cloud optimized point cloud, whether as a like a tile index that points to a bunch of tiles, or a single giant one, although that's maybe not the best way to go about it. Or you have entwined point tile, which might represent a county or a multi-county statewide collect. They map to the USGS collects. The ability for TileDB to then be able to go ask that point cloud, hey, I want to select for this window at a particular resolution, maybe because Kyle was showing the being able to inspect the point cloud data before, going off and doing a bunch of work. Like that's a key sort of assumption that is we are able to take advantage of that Fusion wasn't. And so that kind of changes how we approach the problem as well.
Yeah, so it's like I can look at, I mean, the USGS data set, for example, is all in EPT and all stored in S3. And so I can easily, reference, an S3 bucket or an S3 item, and pull that down incrementally. So it's like you're not pulling it all down into memory at once. You're pulling down one little chunk, and then and which also makes it much easier to do it in parallel. So you can pull down 10 different chunks of this COPC data, run your operations over those 10 different chunks, and then just ship it off to TileDB and also in S3. And so it's like I kind of just pull stuff down from S3, run my little operations over it, and then push it right back into a different S3 bucket. And it makes it really flexible, makes it a lot easier to work with stuff from your own, personal laptop. Because I mean, data is only going to get bigger. Storage is cheap, and there's hundreds of terabytes of data available to you on S3.
Another thing that we worked hard to support was everyone has their own pet metrics, I think you would say. And so, working with Bob, certainly we learned a lot about it. We are not forestry people, really. We are not forest modelers. Like we know lidar data, and the part about lidar data that we really know a lot about is how to deal with how big it is. But it was clear that being able to support kind of a custom metric that is defined as a Python script, that's a feature that none of the other tools really have available to them. And if that's important to you, or if it's in a lot of cases, it's just tell me how this thing was made, and that itself is valuable. And so, that was something that we worked to make sure we had implemented. And the other thing was trying to get these tools into an audience of whether they're early career researchers or data scientists or somebody who is used to a different software suite about how they go about their problems, being able to handle the data part of it to the point so that people could move forward with the interesting part.
And one more quick thing I think is worth mentioning about the metrics is that our metrics are serialized and stored in the database. And so if you create a custom metric and you want other people to also be able to write to your TileDB array, they don't have to have your stuff available to them. They can deserialize that method and run it from their own laptop if they like.
With a few caveats. But...
With a few caveats, yeah.
Have you had any well, let me have you had any issues with managing vintage of lidar as far as compatibility between algorithms?
I have not personally, no. What kind of problems do you foresee?
Well, for in the forestry sector in general, the time story is kind of one of the most important things. But the more many metrics break or are developed for single vintages of lidar, which are getting better incrementally. But there are things that absolutely break on the changes in the collection methods and actually the changes within some collection environments like lidar that is collected with intensity normalization set to some
Oh,
component will basically lose data. Like in
yeah.
California, there's an issue with chaparral that appears to be ground because it in certain settings if the power of the lidar beam isn't high enough. Or there's other generations of USGS data that have poor alignment in areas in which they're out of the near nadir track, and so they have these ghost Ghost ground returns that are poorly aligned with the classified ground, which are obscured from most users, which cause mayhem in like ladder fuel
Yeah.
estimations. I mean, frankly, I feel like we're into maybe the 6th generations of lidar, and the old ones, you get different nuanced effects that kind of prevent from my perspective, like the ability to assume that a collection is something that doesn't have to be manually inspected is kind of this
Yeah.
Yeah,
remains.
we're not solving all the world's problems, though.
No.
We're barely solving our problem here as far as the data management one. But I mean, yes, you're still going to be very sensitive to the data that's in there, and I don't think you get to avoid that. Um, but the hope is make it more convenient for you to bring your tools to bear on it. I think that's kind of mostly what we're going after with SilviMetric, and also make it easier for people to go pour a lot of computing at it without having to essentially construct all of that yourself.
And I mean, as long if you're, familiar with like if you're good enough at using, Poodle pipelines, there's a lot that can be done there before SilviMetric really even touches it. And so, I mean, that doesn't have to be like a pipeline doesn't have to be carried over between data sets. So it's like you can write a new pipeline for each data if you want, really. I saw there was some chat. How do I check the messages in Zoom? I didn't see if anybody had questions in there. Oh, there we go. Oh, okay. Just Howard.
So a couple times you've mentioned partnership with USGS, particularly as noted by the sites that are accessible in visual form through their entwine.io site. I'm curious how deep that partnership goes. Have you already been through a majority of the processing on those to build that
Oh,
TileDB, or no?
no. So we were
Okay.
just starting to get to that point, and the vehicle that we were using was shut off. And
Okay.
so that's where it is at the moment. So,
So that
hopefully
definitely is
there's,
something we envision.
yes. And, we have done nationwide processing of that EPT data for other things. Like we produce if you've ever used Planetary Computer, there's a height above ground surface in Planetary Computer that's available. It's like a 2-meter product. We had produced that, so we have experience doing nationwide processing of this, and so we kind of know what the cost structure and the problems are with doing those kinds of things. And so, we kicked around maybe doing it commercially, but we don't really think they're the customer for that because it has to be constantly updated as more data keeps coming through the pipe, and having a customer base and enough of a tail to do that maintenance is pretty difficult. At the moment, the software I would say is at the interesting and probably useful stage, but needs to be proved out at scale. So we're looking for partners to help us with that. If you had a large forestry, national forest size thing that you wanted to work with us on, we're looking for somebody to help us kind of prove that out and help us kind of realize the vision here. And or one of the national forest agencies, probably not the one in the US, jumping in and going, hey, this is important to us for our own management strategy, and we're interested in it.
Well, I might not be able to deliver the US, but maybe would you be willing to let me follow up with you offline? State of California has several sets of or has interests along these lines for our large scale forest and vegetation management activities. Tim's definitely familiar with it, and it's by way of him that he introduced me to this session going on today.
Okay. Yeah, we certainly are. Like I said, we're just kind of floating in our boat at the moment, looking for a little bit more propulsion. But again, I mean, that's one of the advantages of an open source model for this. You know, maybe activity stops for a while, it can get picked back up, and kind of be able to move forward.
One of the things, I'm going to circle back to my first comment. One thing that has emerged within kind of the U.S. Forest Service's technical expertise has been this concern and I think institutional stress that new methods and algorithms present to them as in their decision processes, and the continuity and stability of analysis methods is like actually kind of a really important kind of design component. And so like looking back at these processes as actually supporting core analysis and science that's been done over, I think Bob McGaughey got started probably 30 years ago on some of this stuff is actually like it is that continuity has extraordinary value, and especially in this space where there are pressures to adopt new flashy technologies without necessarily optimizing the tools that we've had kind of emerging for a while.
Yeah, I mean, one of the lessons I really learned with the AWS public data sets is how I expected people would use that content and how it's actually used. I mean, some of the things that I expected would happen are there, but all sorts of other uses creep out of the woodwork once it becomes convenient to touch national scale data with, just be able to throw computing at it. And so for the point cloud data, there's companies doing things like, tower siting and insurance and roof measuring and all of this stuff that was really hard to do if you had to do all the data management of it yourself and apply your algorithms to it and apply your quality control and whatever your magic sauce is as well. And so these kind of technologies that try to sit in a space where hey, let's just try to solve the massive challenge, the challenge of the massive data in a way that provides convenience for people to do the things that they're going to want to do with it quickly and conveniently, has a lot of value. It can generate lots of cost, obviously. So it depends on who's going to bear that cost. Now, for the public data set, we were able to get AWS to bear that cost. Although the cost of processing it has actually been USGS. It's the one who pushes that content, but then AWS kind of manages and assumes the cost of its distribution and access. And other clouds are doing that too with the point cloud data. I could see a similar sort of thing happening with like a SilviMetric sort of forestry oriented data set as well. But need resources to get to that point at the moment. And collaborators too. So if this is interesting to you at the smaller scale, you're not looking to do national data, you're looking to do grid metrics in Python. I mean, in the end, that's what a lot of people just want is grid metrics in Python and not have to deal with 94 raster files from Fusion or whatever it might be. This does that too. So if you're looking to collaborate smaller scale, get on our GitHub, start kicking the tires and making tickets at us, and I will answer.
Yeah.
Has a plot scale analysis come up as a use story instead of going to grid metrics, extracting point clouds that are defined by, like often we're using cylindrical volumes, and I just did a project of 180,000 plots for a bitemporal lidar project, but that user story kind of varies significantly from the grid metrics style approach and I'm curious, is this on the roadmap?
It is. So I mean, like Howard said, we are not necessarily forestry people. So I've been kind of become more introduced to a lot of the kind of approaches that are available within forestry. I just went to SilviLedarr about a month ago and learned quite a bit about this. So no, the plot stuff has not been something that I've implemented or tried yet, but it is definitely on the radar. And so I think that's just something I need to learn more about and how I would actually implement it in SilviMetric. But I do know about it, and I am aware that it's kind of a pretty prevalent approach for analyzing forest plots, I suppose. Yeah. Because I would actually say that a lot of the people that I met at SilviLedarr were doing we're not doing like these massive point cloud uses, but we're doing more like we have 10 stands in northern Quebec where we're of like 400 square meters or something like that. So yeah, it's definitely something that's on the radar, but I haven't thought about how to implement it yet.
How about I've asked this question to Howard in person before, but what about the discrete grid approaches like H3, S2, A5?
Oh,
for the shadow?
So, I mean, it would be possible to organize your data according to those grid cells in TileDB if you wanted to. So instead of square grids, you could use hexagons, whatever the heck shape an A5 is. Those are weird shaped. So, I mean, they're just arrays, right? So you could still do it that way if you wanted to. We don't have anything implemented that way at the moment. Been experimenting with.
Yeah, sorry, go ahead.
We've also been experimenting with discrete grids for doing just data distribution, just because of the convenience of everybody having the same reference system. But yeah, it's just arrays, right? So
Yeah. I mean, that is certainly something like that you could just SilviMetric doesn't have this approach yet, but that is certainly something that you could do. Like rather than doing like XY, you could just have like an H3 ID and a resolution associated with it, and then you can just query by that instead. And I mean that's certainly an option. Though we are kind of in the grid the like square grid approach. Yeah.
I mean, our initial contract was, work with Bob to kind of extract out grid metrics to something that could exist as an open source project and could move forward and maybe potentially attract a collaborator or contributor base and attack this problem of kind of infrastructure grid metrics.
Awesome. Kevin, you got any questions? Okay, well, I will close the recording. And thank you so much, Kyle and Howard. That was really great.
Yeah, thanks for having us.